Washington and Brussels are in the midst of a policy funk over the possibility that China's industrial policies could do to the market for legacy chips, or what some in the industry prefer to refer to as mature node semiconductors, something similar to what happened with photovoltaics, PVs, over the past decade, and potentially to electrical vehicles, EVs, over the next decade. Namely, fears are rising that there could be overcapacity in semiconductors of the mature variety, a fear partly animated by seeing how Chinese subsidies on steel and PVs have affected global markets, generating a desire to be proactive in trying to address future potential areas of overcapacity. And to be sure, Beijing has provided subsidies across the semiconductor supply chain, including to mature node manufacturing firms. The core concern is driven by China's current plan to build mature node fabs and the conclusion that this will result in overcapacity. The reality is more complex though, because mature node semiconductors, it turns out, are very different from either PVs or EVs. In fact, this may not be the overcapacity problem anyone is looking for. Title 1: The Market Globally and in China. Let's explore why concerns may be misplaced by looking first at the global market structure for mature semiconductor production, and then at China specifically. The industry prefers the term mature node to legacy chips in discussing the topic. Mature nodes are typically regarded as those produced at nodes at the 28 nanometers, nm, level or above, the definition that the Commerce Department as part of CHIPS Act language and Bureau of Industry and Security, BIS, has used in requesting input from U.S. companies about their use of China-origin semiconductors. Semiconductors produced with these more mature processes are typically made at facilities where the equipment costs have been fully amortized, but they involve much lower profit margins than the most advanced semiconductors. These include central processing units, CPUs, graphics processing units, GPUs, and other application-specific integrated circuits, ASICs, that are used in smartphones, for training AI models, or for other applications demanding high levels of performance and low levels of power consumption. Typically, memory chips are not included under the term mature, because most memory is produced and sold at more advanced nodes, where capacity, speed, and density are at a premium. There are 4 critical basic elements of the market for mature node semiconductors that are relevant to the debate regarding overcapacity. First, the term mature semiconductors covers a range of different types of chips, each with its own supply and demand dynamics. These include both specific types of semiconductors, including logic, power, radio frequency, and mixed analog and digital semiconductors, and mature semiconductors used for specific types of end uses, such as automobiles, robotics, drones, industrial automation, aerospace, and other industries. Hence, there is no single market for legacy semiconductors, as there is for products like EVs and PVs. This makes overcapacity an inappropriate lens through which to view the issue. For example, aggregating capacities for fabs in a particular country based on process node does not account for the diversity of applications and requirements that semiconductors manufactured at a particular node actually cover. Second, most mature semiconductor node capacity globally resides with so-called integrated device manufacturers, IDMs, while in China the capacity for mature node production is dominated by companies engaged in foundry services, which includes a high degree of specialization. Foundries build semiconductors based on designs provided by their customers. These are contracted levels of production and depend on market demand as determined by the customer of the foundry, not the foundry itself. Company-designed semiconductors are closely aligned with the demand in their particular sector, and they seek to carefully balance supply and demand. In fact, their business models are designed to avoid overcapacity, meaning overproduction that has tended to be more common with IDMs. Foundries tend to be highly specialized, and often each fab facility that is operated by a company will be set up to address a very specific client product. Hence, aggregating capacity numbers at specific nodes does not indicate the supply and demand function for specific types of semiconductors produced at those nodes. In China, based on the author's discussion with industry officials, the expansion of manufacturing capacity at mature nodes by 2030 will be dominated by foundries. In 2023, the foundry/IDM split was roughly 60/40 and is projected to be 64/36 in 2030. Third, because it is difficult for foundries, which for mature node semiconductors operate on very thin profit margins, to rapidly switch production lines, foundries and customers prefer to engage in long-term contract arrangements to lock in supply for a specific type of semiconductor. This holds, in particular, for industries with long product life cycles and high levels of safety requirements necessitating stringent qualification of product quality and reliability, such as medical devices and automotive applications. Fourth, and perhaps most important, is the often overlooked or misunderstood concept within the industry of economic overcapacity. This refers to the idea that the global industry actually views a certain amount of excess supply as desirable and critical to smoothing out anticipated and common perturbations in supply and demand. Some of these risks include tool downtime, which is unpredictable, natural disasters, such as the Fukushima earthquake, which affected front-end manufacturing and material suppliers, the winter freeze in Texas that impacted Samsung, and other accidents such as fires at key facilities that have occurred over the past several years. Some in the industry hold that an optimal level of overproduction is around 15 to 20%. Even after the major chip shortages during the pandemic, there continue to be rolling shortages for some mature nodes, and the health of the overall system requires some level of economic overcapacity. Finally, focusing on things like fab utilization rates may not be a good proxy for considering where there might be overcapacity that could translate into the potential for dumping, which is defined as exporting products at prices lower than they are sold in the domestic market. Fabs involve a lot of complex tools operating at high speed, and require a lot of maintenance. For example, utilization rates can vary from 70 to 90%, depending on the node and critically, on demand. During the chip shortages during the pandemic, some fabs were working at 99% utilization rate. They were running tools too hard, too fast, and for too long, a condition which is not normal or desirable. But the circumstances required it. But this situation did not lead to overcapacity or dumping. Only if a fab is, say, running at 99 to 100% utilization for 2 to 3 years without a broader global supply chain crisis should government officials be worried about a high utilization rate leading to potential dumping. Title 2, China and the Worries About Overcapacity. Understanding what is driving the expansion of China's foundry capacity is critical to getting at the issue of whether overcapacity is likely to happen in mature semiconductor production. A number of factors at play highlight the difficulty of a situation where Chinese companies, either foundries or IDMs, could flood the market and drive down prices, disrupting markets. Currently, Chinese firms account for a growing share of global front-end manufacturing for mature semiconductors. This market share differs by node, with around 27% for 28 to 65 nanometers process node production, falling to around 20% for 90 to 180 nanometers. If the current announced fab capacity expansions are realized over the next 2 to 5 years, then by 2030 Chinese companies may hold a larger share of global capacity, but it is hard to be sure since there will also be major capacity expansions for both mature and advanced node semiconductors in the United States, Japan, Taiwan, South Korea, and Europe. There are 3 reasons why overcapacity concerns are either exaggerated or misunderstood as emanating uniquely from China. First, production expansion goals are different. The goal for Chinese firms expanding capacity, such as SMIC, Huahong, Grace, Huali, CN, and many others, is to supply primarily domestic demand. With China still importing a huge majority of its domestic semiconductor consumption needs, there are commercial drivers for expanding domestic capacity. U.S. export controls have also accelerated this trend, both by preventing companies like SMIC from being able to focus on advanced node production and by spurring the Chinese government to encourage companies in China to seek domestic alternatives to foreign suppliers for both hardware and software across a range of government organizations and industrial sectors. SMIC, for example, has gone from having 60% of its production for foreign customers 5 years ago to nearly 80% of capacity now used for domestic customers. Close to 80% of Huahong production is also for domestic customers. This is very different from PVs, for example, where the target from the beginning was the export market. Second, demand is key. Most of the commentary on China and the potential for overcapacity in mature semiconductors focuses on the supply side, that is, extrapolating the capacity expansion that will result when all the mature node fabs under construction are completed within the next 3 to 5 years. But the key question for semiconductors is demand. Domestic demand in China remains high and will only increase substantially through 2030. Projections of demand based on specific sectoral applications, servers, PCs, mobile devices, autos, industrial sectors, etc. matched against capacity at specific process nodes, 28, 40, 65, 90, 180 nanometers, provide a way to assess whether and when signs of overcapacity could become real. One non-public industry study seen by the author, for example, showed that by 2030, assuming all of the announced fabs in China are actually built and operating by 2030, domestic capacity will be able to cover around 90% of domestic demand, including Chinese OEMs, and foreign OEMs with factories in China. This number was around 37% in 2020. Third, the benefits of government support are not starting to show yet. Concern about China and mature node semiconductors centers on how the potential benefits of Chinese government subsidies could accrue to Chinese foundries and the potential for this to contribute to overcapacity. In assessing this issue, it is important to note that for leading Chinese foundries such as SMIC and Huahong, their margins, capex, and depreciation compare favorably with industry averages. With the global semiconductor industry just emerging from a major downturn, for example, all foundries, with the notable exception of TSMC production at advanced nodes for products like NVIDIA GPUs, are experiencing low utilization rates, are trimming prices to gain orders, building fabs with high levels of depreciation and experiencing low margins. Again, SMIC and Huahong's financial performance levels are generally consistent with industry averages, so it is difficult to say that SMIC is cutting prices because the firm is receiving government subsidies or that they have a higher margin because of government subsidies. In addition, even if under some circumstances Chinese foundries could offer below-market prices for mature-node semiconductors, the cost of these semiconductors is already relatively low, so there would be little incentive for domestic or foreign companies to boost ordering from China-based foundries. This also holds because semiconductors are intermediate products, purchased by original equipment manufacturers, OEMs, unlike EVs or PVs. In addition, domestic OEMs are not likely to be responsive to slightly lower prices offered by SMIC or to Chinese government exhortations to source semiconductors domestically. Most, but not all, Chinese OEMs are market-driven and globally competitive, and they are also interested in other factors such as reliability and quality. Foreign OEMs may be responsive to lower prices and government-driven local sourcing requirements, as they must compete with Chinese semiconductor firms and local OEMs. Here the "in China for China" approach is a trend for foreign players. In addition, the quality of mature-node semiconductors from Chinese foundries for specific end uses varies considerably. Products from these foundries are getting more competitive for some consumer electronics applications but remain significantly less reliable for end-use applications such as automobiles. Here, foreign firms like NXP, Infineon, Renesas, and Texas Instruments will continue to hold dominant positions in the China market. Chinese domestic firms are becoming more competitive in some auto industry semiconductor segments, such as powertrains, but lag significantly in other areas like ADAS platforms. Finally, while Chinese foundries do lower prices in ways that put pressure on non-China-based foundries, PSMC, for example, does compete directly with Chinese foundries in areas like specialty memory and display ICs. Lower prices are not only a direct result of government subsidies but are more likely to result from things like better cost control. In addition, some fabless firms and OEMs welcome lower prices and diversified manufacturing sources driven by healthy competition. Title 3, Looking Ahead, US and EU Concerns about China. With officials in both the US and European Union taking a hard look at the potential for overcapacity in producing mature nodes and attempting to craft policy responses, it is important for policymakers to understand the complexities of semiconductor supply and demand in general. Determining if there is actually a problem requires understanding Chinese companies' position in global and domestic value chains in particular. The U.S. Commerce Department in the first quarter of 2024 surveyed around 100 U.S. companies to determine their dependence on Chinese firms for mature semiconductors. The dependence issue is tightly coupled to the overcapacity concerns, as U.S. officials are concerned that overcapacity could lead to greater dependence, and hence vulnerability of companies to disruptions in mature node supply chains. The situation is also complicated by the large number of finished products that are assembled in China by foreign firms, including U.S. companies that incorporate mature semiconductors. U.S. companies import few individual semiconductors, but rather products containing one or many mature semiconductors that could originate in China, both from domestic and foreign foundries operating in China. Because of U.S. export controls and the growing pressure in China for certain government and state-owned enterprise-based supply chains to reduce the quantity of foreign-sourced semiconductors, the proportion of China-origin mature semiconductors winding up in IT products manufactured by foreign companies in China is likely to rise. For example, new guidelines on government procurement for PCs, laptops, and servers released in a draft last August were followed by implementing documents in late December by the Ministry of Finance, MOF, and Ministry of Industry and Information Technology, MIIT. They were accompanied by a whitelist of domestically approved secure and controllable processors issued by the China Information Technology Security Evaluation Center, NITSEC, a technology evaluation organization closely associated with China's security services. The NITSEC whitelist includes processors from Huawei, Phytium, Luxong, and Zhaoxing. The first three companies are on the U.S. Commerce Department's entity list. The procurement efforts in these types of guidelines have typically been governed by internal documents, marking this as what appears to be a rare instance where such guidelines are being made public. The effort is part of a process known internally to China as Xinchuang, meaning Information Technology Application Innovation. The new guideline was characterized by a local government official as the first national, detailed, and clear instruction for promoting Xinchuang. In addition, SOEs have been instructed by the State-Owned Asset Supervision and Administration Commission, SASAC, to work towards a 2027 date to transition to domestic suppliers for all technology requirements, presumably meaning both hardware and software for products such as computers, laptops, and servers, and likely more and more mature semiconductors will be included on whitelists, as domestic production increases and the levels of quality also improve. Given this process, which can also be seen as protectionist and a non-market practice that has clearly generated considerable concern with the IT sector broadly, the domestic demand curves in key application areas for mature node semiconductors are only set to rise, a process also undercutting the idea that the domestic semiconductor production will reach some level of overcapacity anytime soon. This will not stop governments from being concerned about the potential for overcapacity, given past experiences with PVs and the current concern over EVs. But semiconductors really are different. That said, the scale of the subsidies provided to Chinese semiconductor manufacturers and the sheer scale of the growth of domestic mature node capacity are significant and have generated valid concerns within the semiconductor industry and in Western capitals. In assessing the implications of this massive expansion in China, it is important to remember that companies outside of China in the mature node sector are not standing still. Global foundries, and Taiwan's TSMC and PSMC, for example, are increasing production capacity for mature nodes in the US, Singapore, Japan, Germany, and India, providing a diversified mature node footprint to balance some of China's natural growth. For Chinese companies to win in the mature node semiconductor space by 2030 requires both easing of geopolitical tensions between the US and China and the ability of Chinese OEMs to deliver a cost advantage. Under this rosy scenario, for example for the auto sector, Chinese OEMs building EVs and other related IT products that use mature node semiconductors gain significant global market share and demonstrate that using mature semiconductor node products from Chinese companies provides significant cost advantages and drives increasing adoption by incumbent OEMs. This would mean that China-origin mature node semiconductors are used in products sold in both China and internationally. The opposite scenario is basically the status quo. Chinese OEMs continue to gain domestic market share but fail to gain traction outside China, as geopolitical tensions override any cost advantage. Here, China-based mature node semiconductor companies gain a share only among Chinese OEMs, and global OEMs continue to prefer products from incumbent mature node semiconductor producers. Hence, the bifurcation between the China market and the rest of the world seems more likely than China creating overcapacity that swamps global markets. Available estimates of the balance of capacity and demand to 2030 suggest that even with the significant growth in domestic capacity, satisfying the huge increase in domestic demand will remain the focus of Chinese foundries. Any policy response related to concerns about overcapacity in mature node semiconductors must take into account all of the above factors. In determining if there are valid and sufficient reasons to believe that by 2030 there will be anything resembling overcapacity, governments must be very careful and fully understand the complexities of the industry, on both the supply and demand sides of the equation, which are considerably different from EVs and PVs. Policymakers in the US and the EU should draw on industry expertise to understand the directionality of markets for each technology node and seek industry input on particularly difficult areas to get reliable data, such as demand projections to 2030. Without a thorough understanding of the industry, supply and demand, commercial considerations, regional and geopolitically driven commercial preferences, and technology roadmaps, it will be impossible to determine whether there is, in fact, a problem and to determine what measures to take in response.